Okay, before we talk about atomics, I want to define the terms that people keep using in multi-threading systems and CPU architecture. If these words are not clear, then atomics will look like random API name. Atomics will look like magic. But if these concepts are clear, then atomics become very logical. So I'll first define the key jargons from the point of view of C++ compiler behavior, CPU execution, and hardware memory visibility. Okay, so right now I'm not writing anything. So if the screen remains stuck, don't worry, because I'm not writing anything yet. Okay. Okay, so what is a thread? So that is the first thing you should understand. So a thread is a independent sequence of instruction that can run concurrently with other threads. So let us understand this clearly. You have a, let's say, CPP file, and then when you compile this, you get object file. This is the machine code which the machine can understand. This is the binary, and when you run this, if this is your computer, it has OS, and it will allot some resources to your program, right? And when it is running, it is called process. So the process is the running instance of your program. Now let us imagine your CPP program has a function main. Okay, so right now your process is running on a single thread, which is the main thread. Okay, so this is one thread that you are currently running. Now imagine if at this particular moment there is a need to get input from the console, or input file from the file stream, or some socket request that you need to do. So at that moment the CPU will be idle, right? Because the thread here is not doing any work, so the CPU will be idle, meaning we are wasting CPU cycles. Okay, but ideally the case that we want is, we wanted that there should have been another executing thread. Let us assume that if we have another path that is parallelly executing, then the CPU would not have been idle, right? So in a process, if you see, in a process, if we can have this kind of system, this kind of mechanism, that if multiple threads are there, then we are going to save our CPU cycle. CPU cycle means time, and time resource is very important. Nowadays we talk about low latency, we talk about ultra low latency, right? So this time is very important parameter. It's a very important resource. So yeah, so that's basics about thread. We will go in detail as we go through the lecture, but this was essentially a lecture on atomics. But since I wanted you guys to take it from zero to hero, and that is why I'm touching upon these very fundamental details. And just for letting you know, this is called the fork point. Okay, next let's understand what is shared memory. So whenever a thread is launched, a thread gets its own stack. So let us assume that if you have a program and you launch a thread T1 here, T1 gets its own stack space. When you launch a thread T2, it also gets its own thread stack. Okay, so this is very particular to T1, this is particular to T2. There are no shared space. They are, the spaces of T1 and T2 are mutually exclusive. Okay, but there can be some memory which is shared among T1 and T2. It can be a global, let's say a global variable, a global function, and whatever. I mean, uh, shared memory basically means memory that is accessible by more than one thread. And so now this is where the concurrency problem begins. If a variable is local to one thread only, there is usually no synchronization problem, right? But if two or more threads can access the same variable, and especially if one of them is right, then we need to reason about the correctness, right? We need to reason about the ordering, we need to reason about the visibility, and so on. So shared memory is the whole reason atomics, mutexes, and memory ordering exist. So we will understand atomics, memory ordering, visibility, all these things in detail. These are not just general jargons, these are very technical terms that we will understand. Okay. Okay, so that is about shared memory. Okay, next let us understand what is cache. So imagine that you have a CPU which consists of multiple cores, and then you have your hard disk, right? And then you have RAM. Then you have, if it is, let's say, core 1, this is core 2, this is core 3, you have a memory that sits on the core, and this is private to this core. Then you have this, then you have this. Okay, and imagine you have one more memory. I will say it level 1. Okay, and this is level 2. Then there are some registers which, if you see, is proximally the closest to the CPU. So these are basically the registers. So if you see, the registers are the closest to your core, meaning to access a data from register, it will hardly take close to one operation or one CPU cycle. Accessing from L1 is almost like is almost like 2 to 4 CPU cycles. From L2 you will have close to 10 to 15 CPU cycles, and then let's say you have a shared L3 cache which is shared by all the three CPU cores. So L3 would be around, let us say, 40 to 50 cycles. This is your RAM. This is, let's say, this is 200 to 200 cycles. So these are approximations. They depend on the clock speed, but this is a good approximation that I'm referencing from a very popular book. So you can assume that these are correct, and these numbers can be cited in an interview. And then we have a disk which is like the cycles go in K. Okay. Now if you see, if the CPU wants to do some operation, then what will the preference of the CPU? The preference is that CPU want all its data inside cache, because cache is the closest to CPU, and obviously from cache it then takes the data into registers and it does the operation, whatever logical arithmetic operation it has to perform, right? Okay, so if I put it in a very formal manner, then a cache is a very small and a very fast memory which is close to the CPU core. It stores copies of frequently accessed data so that CPU does not have to go to the main memory every time. Caches are very critical for performance, if you see by the number of cycles, right? But caches also create complexity in multi-threaded programs. For example, two core, let's say this core C1 and C2, may hold copies of the same memory location in their cache. So when one core update a value, the other core may still temporarily have a older copy, right? Let's say if this L1 core, a thread running on L1 core was updating some value. Now it has updated that value on the cache. This cache belongs to core 2, but that same value might not have been updated here, right? So you see that the coherence between the caches is violated. So although cache are very much important in terms of the time, but it also creates complexities. Okay, so and this is and that is why hardware needs a cache coherence mechanism, and it is also why synchronization also matters. And so I just quoted example, right? Suppose you have a x which is stored in memory. Let's say this core 1 loads x into its cache, and core 2 may also load x into its own cache. Now both cores have their local cached copies, right? Now operation performed by these cores would be on these local copies, and when they would be updated in their respective caches, for some moment we would be having uh, we would not be having cache coherence, because there may be that the value stored in L1 cache of C1 is not equal to the value stored in L1 cache of C2. And so this is a problem, right? And and we need some kind of synchronization. We need some kind of standardization that enforces the coherence. So all these things we will see later, and right now we are just going through some of the jargons. Okay. Next, I wanted to discuss about cache line. We already discussed about cache. Let us understand what is a cache line. So a cache line, if I put it formally, is a unit in which data moves between memory and cache. So you have your RAM, which is your main memory. You have your, let's say, L1 cache, and it would have some lines, and the size of this line will depend again on the hardware you are using. Let's say if we have a 64-bit system, meaning the length of the cache line is 64-bit, and so this means that CPU does not move a single variable by itself. Example, if CPU is reading a variable from, let's say, some memory here, then it is not just reading this block, it is reading the whole block that is equal to size of its cache line. So the CPU is actually reading a 64-bit block from here, and it is loading into its cache line. So not only it moves the particular variable, but it also moves the nearby bytes. Now this becomes very important for performance, because let us assume let's say when two unrelated variables may fall on the same cache line. Okay, so let us understand the scenario. The scenario is very important. Let's say you have two variables A and B. They are not related to each other, but let's say the core 1, which is running thread 1, reads A, but since B is in vicinity of A within 64 bytes, so 64 yeah, bytes, this would be bytes, right? Okay, so it will load here, A and B both will be loaded. And yeah, where was I? Yeah, so now we have two unrelated variables which may fall on the same cache line. And now if different threads, let's say this T1 was there, right? Let's say we have T2 also. If T1 is interested in updating A and T2 is interested in updating B, then if these two threads keep updating those variables, the whole cache line may bounce between cores. So for example, if T1 is updating A, it will load A, update the A, and it will also load B. Now when T2 is updating the let's say B, it also again loads A, right? So basically what we had earlier will be invalidated when T2 loads it, right? Okay, so so if two int variables sit close together in memory, they may be part of the same 64-byte cache line, and in technical term this is called fault sharing. Okay. Okay, so let us now move to cache coherence. Okay, so a cache coherence is basically a hardware mechanism which ensures that different core, right, and that cache lines C1, C2, L1, L1, so different cores uh, eventually agrees on a value of a memory location. So if core 1 writes to a value, and core let's say if core 1 writes to a value, it has some, let's say, variable x, and core 2 was having some earlier copy of x dash, uh, then coherence machinery ensures that core 2 stale copy gets invalidated or updated according to the protocol, right? So it will be updated, and these both should reach a coherence. And now there are different protocols for that. Common protocol family is Mazy protocol, which is modified, exclusive, shared, invalid. That will be seen in detail in later lectures. So that's all about cache coherence. And one important thing, so coherence gives eventual consistency of memory location. It does not by itself mean immediate visibility of all writes, and it does not give even higher level ordering guarantee across multiple variables. So the visibility and the ordering guarantee, it does not give in the immediate effect, right? Eventually it is going to be consistent, and this distinction is very important. So we talked about the immediate visibility, and we also talked about ordering guarantees. Okay, so these things are very important. We are going to study them in very detail when we will studying atomics in detail. So, and the other thing that I told was, so coherence gives us eventual consistency. Okay, now let's see. Okay, let us see one more concept before we actually dive into atomics. Let's see what is compiler reordering. Actually, we are going to read more than one concepts. I have a few jargons in my mind, and that I wanted to explain. Yeah, so I created I thought that I will directly jump to atomics, and will explain you in detail, so that if you're going for an interview, then you can actually explain them atomics in great details, be it from HFT perspective or EDA perspective, or whatever. But I thought that it's better to first clear all the jargons. We should be on the same table before moving to the war room. So what is a compiler reordering? Compiler reordering means that let us say if you have two expressions, a is equal to 1, b is equal to 2, these are not related, and since these are not related, the compiler may reorder or rearrange the instructions, right? So a compiler does not think in terms of that the programmer wrote line 1 before line 2, so line 1 must physically happen first everywhere. The compiler actually thinks in terms of language rules, and and allowed optimizations. So the compiler will always refers to its rules plus optimization. It will not think from the programmer perspective. So if two operations have no visible dependency in a single threaded model, the compiler may change their order. Now, why does it matter? This matters in multi-threading because let us assume another thread may observe result in an order different from what source code suggests. There it can cause a problem, right? So there we would be needing synchronization, and whether that we are going to achieve using mutexes or atomics, that we'll see. Okay, so this was about compiler reordering. Let us now look at CPU reordering. So a CPU reordering means that the processor may execute memory operation in an order different from the program order to improve performance. Again, it is about optimization and performance. So the CPU might execute operations, memory operation, in an order different to what programmer may anticipate. and mostly our modern CPU are out of machines, sorry, out of order machines. You can read about this. And so basically the modern CPUs tries to keep the execution unit busy. So they may issue execute or complete operation in a different internal order. So that is totally acceptable with the modern CPUs. They may go for out of order execution. So that is the thing. So there are two distinct source of reordering that we have saw. We saw the one is compiler level and the another is CPU level. And for our understanding, both of them matter. Let us take an example to understand this a little better. Let's say you have a data to let it be 10, and you have a boolean flag which is true. Imagine this is a callback. This is a function, functor, lambda, whatever it is, and let's say t1 acts on this. And if there is some kind of reordering, then first t1 will look at data and flag, and t2 might look at flag first and data second. That can be the case. So this t2 might observe flag as true before data 10. Okay, so it what I mean is t2 will say that okay, I saw that flag is true, but this data is not 10. So maybe earlier data was 0, and so t2 says that flag is true but data is not 10 because this operation hasn't happened yet. Okay, and so yeah, so that's about reordering. We will see in great details how mutex solve this problem and how atomics solves this problem beautifully and inherently. Okay, so for out of order execution, I already discussed that the so the modern CPU have these techniques where instructions are executed when their inputs are ready, so not necessarily in source order, right? So this improves the number of requests per unit time, basically improving the throughput, because now the CPU is not stalling the pipeline, which may have different stages of operations going on. Now that the CPU will not stall waiting for one slow instruction if it can do other independent work meanwhile. Okay, so but for concurrent programming, this means uh, the naive instruction, the naive assumption that we have that instruction execute exactly in the order I wrote them is very wrong at the hardware level. Okay, so CPU may internally execute operations in a different order, and the memory system may expose those effect differently across cores. So that we need to see that what are the issues that may come in concurrent programming. Okay, now let us see one very important concept: store buffer and load buffer. And one more thing, if you feel that I am not explaining in great depth, then that is purposely I'm doing that because I wanted to make a lecture on atomics. Atomics we use in great depth in my company, and but to make you understand atomics, these terms, these jargons you have to understand, because otherwise atomics would be very magical to you. Okay, so but if you guys would need detailed tutorial on all these jargons also, so every jargon that I'm explaining right now itself has the potential for a 30 minutes video, 20 minutes video. I can do that also, and that actually might help you, because there are just a handful of them. I mean 10-15 of them are there, and they basically bridge the gap between the CPU the architecture and the software. So, and that is very important also, that you understand how when you write a program and how your compiler actually uh, tries to behave, and how it actually is influenced by the architecture beneath. Okay, so I firmly believe that if you are a software engineer, you should have a very good command on the computer architecture. Okay, let's proceed to store buffer and load buffer. So all these are basically buffers. Buffers literally means uh, as a uh, as a storage uh, container before actually uh, going to its actual place. Okay, so let us uh, assume that you have a CPU, let's say, and let me do this. Let us assume this is L1 core, and this is the cache line. This is the L1 cache line, and this core now will have this store buffer. Okay, so store buffer is basically a per core structure. Means every core will have this store buffer where writes are held temporarily. So let us assume that the CPU, sorry, this core has to do some write operation. So before making this write global, it is temporarily hold in the store buffer. Okay, and so it is stored in this whole buffer temporarily before becoming globally visible through the cache coherence system. Right? We talked about the cache. If another core cache coherence. So before actually the cache coherence can work, the values is stored in this store buffer. Now the question that comes to our mind is, why does the CPU use a store buffer? So that is because if every store had to wait until the whole memory system acknowledges it, performance would collapse, right? So CPU must record the write in its store buffer, and it should continue executing, right? It should not wait, until the whole memory system, acknowledge it, right? But because then the performance would take a toll, right? But it comes with some drawbacks. It creates a visibility gap, a memory visibility gap, which we will see later, which is very important to understand if we are to understand atomics, memory ordering, visibility, memory model. So if this is the writing core, and so this writing core knows about the store, right? But this particular core does not know about the store yet, right? So this has not seen the value that has been updated by CO in it. So this is why one thread can perform two writes in, let's say, program order, but the another thread may observe them in a different order, right? The example that we saw earlier, if there are two instructions, one thread might perform in, let's say, the program order only, but the other thread may observe them in some different order. Okay, and this is not compiler reordering. This is about visibility. That the thread 1 has updated data is equal to 10, thread 1 has updated ready is equal to true, but the thread 2 has not been able to observe them in the same order. Thread 2 might see that, okay, ready is true, uh, so I mean the write to ready may become visible to another core before the write to data, because before actually writing out for cache coherence, they are stored in the store buffer, right? So maybe that ready was first stored in the store buffer, and it then was made global, so cache coherence uh, actually happened, but data would still be in the store buffer. It would not have been made consistent, but between all the caches. This may happen, right? So Here the key concept revolves around a term which is memory visibility. So always remember, store buffer, load buffer, they have to do with memory visibility. They are not actually reordering in a concrete sense, if I have to say this. Okay. So a store buffer allows a code to differ, making writes globally visible. It improves performance, as we already discussed, but it is a key reason why visibility and ordering cannot be assumed without synchronization. Similarly, we have our load buffer. So CPU may perform loads early before other operations complete, right? So if, let's say, if you have dependency and memory order rule allows it, then CPU can go for early load before, other operation complete. So what this means essentially is that a core may read memory sooner than a programmer expects, right? Again, this is good for performance, but it means we must reason using the memory model and not the intuitive program order. So for example, a CPU may issue a load of flag before another independent operation completes. Okay. So, and these things will become more clear when we discuss atomics in detail. And again, this is a very high level overview of these jargons. If you want a detailed lecture, just drop a comment. I will just defragment them in the easiest way possible. Okay. So yeah, so as I was saying, that load buffers basically allow CPU to perform the reads early. Store buffer was related to write, and so this load buffer is related to read, and which again becomes a source of reordering that synchronization primitives must control. Okay. Next, which I wanted to discuss was there are a lot of items. Let us discuss this memory model. So memory models basically define the formal rules for how memory operation behaves across threads. And so post C++11 we have a memory model uh, uh, which gives different rules about multi-threading reasonings. For example, what counts as a data race when behavior is undefined, how atomics behave, what is happens before, and how different memory order constraint operations. So all these things. And so without the memory model, multi-threaded reasoning would be very vague, and it would be architecture dependent, right? So the memory model is a kind of formal contract between the programmer, the compiler, and the hardware. So in C++, concurrent unsynchronized access to, let's say, non-atomic variable with one writer is a data race, and data race is undefined behavior because C++ understands using the memory model that you would not, the programmer will not even write an instruction, will not write a program which calls data race. So the memory model, going by the memory model, the compiler will assume that this is not a candidate for data race, hence I can optimize it, and this optimization can be a source of undefined behavior. So that is the thing, right? Okay. So data race is, I think, is very simple. Let's say we have a shared data that is acted upon by multiple threads, let's say 2 threads, and at least one of the operation is right. So, and by memory, going by the C++ memory model, the compiler will assume that the programmer would not write a code which causes data race, and hence I will assume this is not a data race, and I will go for optimization. And yeah, so if it goes for optimization, you don't actually know what's going to happen, and this is a very disastrous situation, right? It's not some race condition, it is actually a undefined behavior, and it's a bug. Okay. So what is undefined behavior? Undefined behavior means the C++ standard imposes no requirement on what the program does. So that does not just mean incorrect result, it means anything can happen, all the bets are off. The compiler may optimize under assumptions that make the behavior appear bizarre in concurrency. This matters because many people think unsynchronized reads and write just risk seeing stale values, right? But in C++, the issue is much stronger. The program has left the boundaries of defined language semantics. You now have a memory model ruling the compiler behavior. Okay, so yeah, so make sure that you don't write program which calls data race on a non-atomic variable, because then it would be an undefined behavior, and it's not a standard data race, sorry, race condition. It is actually a undefined behavior. It is actually a bug. Okay, and yeah, so and the compiler or the language gives no guarantee. Okay, next let us look at atomicity. uh, so atomicity basically means there is operation which uh, at the scope of compiler, at the scope of, let's say, threads, it will look as a indivisible unit. So if an operation is atomic, the another thread cannot observe it half completed. So the competing operations on that atomic object cannot interleave in a way that that breaks the defined semantics. And this is very important for read, modify, write operation like the increment. So without atomicity, instruction that may look as a single instruction is actually at the CPU level is a series of instructions. For example, if you are incrementing a value, it is not just an increment at the CPU level. At the CPU level, you have different stages of instruction execution, because the CPU works on the instruction level parallelism, right? So you may have a read, you may have a decode, and the execute might be happening. So it has different subatomic steps, and the other thread can interleave when those subatomic steps are happening, right? So the other threads can interfere. With atomicity, the whole operation behaves like one coherent step, but with non-atomic simple variables, this is a problem in a multi-threaded program. Okay. Next, there is a jargon which is torn read or torn write. So a torn read or a torn write happens when a thread sees only part of the value update. For example, half old bits, half new bits. So these can happen when object is very large, and then what hardware naturally handles atomically, or when access are not properly aligned or synchronized. So these kind of things happen. So as I said, if let's assume you have a 64-bit value being updated in parts on a machine, and since machine cannot update it atomically, another thread might see a mixed value. So you can have a torn, a read or write happening based on the size of the data. Next, understand what is visibility. So visibility basically answers a basic question that when one thread write a value, let us, so if thread 1 writes a value, when does another thread become able to observe that value? Because in multi-thread, let's T2 comes here. When does T2, which is the another thread, become able to observe that value? And this is not immediate by default. Caches, store buffer, load buffer, weak ordering, all these kind of things affects visibility. So visibility is not just whether a write happened, it's about whether another thread is guaranteed to see it or not, and also under what synchronization conditions. So if thread 1 is writing 10, thread 2 may still read the old value for some time, right? Because I already explained you that the store buffers may come into picture, the cache coherence would not have been completed, all this kind of thing, weak ordering might be there, all this kind of thing might affect the visibility. And it becomes very important when you are working on a low latency system, right? Because for the moment this thread does not see the updated value, which is very much possible in a low latency system that I work on. So this becomes very important that you have a memory visibility, right? You need some kind of synchronization, some kind of mechanism which ensures that you always have a deterministic memory visibility. Okay. Okay, next let's look what is ordering. Okay, so let us assume you have data is 10 and you have a flag which is true. So you might think that suppose a thread T1 does this thing. Okay, now you have a T2 which is acting on the same critical section. You might think that this T2 sees flag is equal to true must also see data is equal to 10. But this the assumption the assumption that you are making that requires memory ordering. Sorry, that requires ordering. Sorry, because without the right memory ordering, another thread may observe the flag first and not yet see the data. Right? It might see a flag only, and for some moment, it might not see the data. That is very much possible. So ordering is not the same as atomicity. Atomicity says that an operation itself is indivisible. So and ordering says that how different operations relate to each other. Right? So without ordering guarantees, writes can be observed in a different order by another thread. And this becomes very important because if the other thread sees this true but does not see this 10, so it may assume the old stale value of data, and that is not the behavior we want. So right, so let's say even though the individual operations are atomic, that does not ensure that the operations are sorry, the ordering uh, yeah, so the ordering is maintained, right? So ordering is not the same as atomicity. Just wanted to clear this up. Okay, and that is why we have different memory models in within atomics. So obviously we are going to use atomics, but along with atomics we are going to use different memory models, which ensures that okay, if you are reading this flag true, the instruction before these have to be written. So all those kind of things we will see. Okay, and these ordering memory visibility load store buffers might seem a bit off when you are reading it for the first time. It happened to me also when I read it about 5 to 6 years ago, but now that it has been daily practice of using them in production, they seems very intuitive, and they would become your second nature. Without them you will have doubts on the program, especially in a multi-threaded, in a low latency, lock-free environment. You These are your friend. Okay, those memory ordering and the ordering, instruction ordering, compiler ordering, CPU ordering, and the memory visibility. Okay, yeah. So we understood this, right? That the ordering defines the constraints on the relative observation of operation across threads, and atomics with different memory order provide different ordering guarantees that we will see later. So all these things we will again go over, but these are just for introduction. Okay, next jargon is synchronization, which I think you are all aware. Synchronization basically means establishing a correct relationship between operations in different threads so that visibility and ordering becomes guaranteed. So mutex lock and lock synchronizers. In atomics we have release, acquire, then we have a condition variable synchronization. So the key idea is that synchronization creates a formal bridge between your threads. Without that bridge, one thread write are not safely communicated to another. Okay, so a mutex unlock in one thread and lock in other creates that synchronization. Okay, so it basically establishes a correct relationship between operations in different threads, so that the most important two points, which were visibility and ordering, they become guaranteed. Okay, so in interviews you should use the jargons that will give away the fact that you actually understand the technicalities. So if the interviewer asks what is synchronization, you should not merely say that when we have multiple threads and we use locking to ensure that we protect the critical section. That is fine, that is the core idea of locking. But what synchronization is actually achieving is it is establishing a well-defined ordering. It is establishing a visibility between the threads. Okay, next let's look at happens before. So again, happens before is one of the most important terms in the C++ memory model. So if operation A happens before operation B, then the effect of A are guaranteed visible to B. Okay, and the required ordering is established. So, and this is the formal way to prove the cross-thread correctness. So in atomics, when we use release on one side and acquire on the other, the acquire sees the value from the release, and then only a happens before relation is established. If you if you cannot identify the happens before path in a concurrent code, then you probably don't yet have a proof of correctness. So yeah. So again, happens before is a formal relationship that guarantees visibility and ordering between operations. Okay, so in multi-threaded C++, correctness is typically proven in terms of happens before. Okay, again, next is read, modify, and write. I think this is pretty much standard. Read, modify, and write. So read basically reads a value, then it will compute a new value, and then writes back. Okay, and this as a whole is one atomic operation. And so this is very different from doing an atomic load, uh, atomic fetch, add, and atomic store separately. Right? If you split it into separate operation, then another thread can interfere between them. But when you have a read, modify, write, this is a atomic single operation, and so they use special CPU instructions which cannot be interleaved by another thread. So the another thread will not have a divisible view of this operation. Next we have next we have yeah, compare and swap. Okay, so again, compare and swap is like this read, modify, write is an atomic primitive that updates a value. So it updates a value only when it matches an expected value, and all these kind of things are the foundations for log-free algorithms. If you want to crack HFT, you have to get used to these kind of uh, algorithms. Use them in your code. Make simple projects. Uh, Start with 5 lines of C++ code. Use compare and swap. Try to visualize memory ordering. Try to visualize memory visibility. Try to see what instructions the CPU is actually decoding and executing when you are using the atomic operations. The more you code, the more you understand. Okay, and so right now I'm not showing you the code.
Okay, so we will see the codes for all these concepts later. I will so all these concepts I will take a simple code and will explain you all these things. Okay, so what is next? Let me check. I made a checklist. I will not go into the different uh, atomic orderings because that would be specialized knowledge of atomics. So for now I'm leaving the sequential, consistency, relaxed ordering, release, acquire, release pair, because all those kind of things basically are the way we enforce memory ordering and visibility, the ordering and visibility. Okay, so next let us see false sharing. What is false sharing? Okay, so let us assume you have a struct. Let's say you have a counter, and let's say you have a int a counter and int b. Okay, so now this a and b are uh, independent variables. If I ask you what is the size of this struct, so this is 4 bytes, this is 4 bytes, together they are 8 bytes. Fine. Okay, now when a thread t1 reads this variable a, uh, it will not just read a, but it will read, so if this is a 4 bytes, it will not just read a, but it will also read the variables which are in proximity of a up to the length of its cache line. This we already discussed, right? So assuming a cache line of 64 bytes, it will read a whole lot of uh, memory, and it will load into its cache line of 64 byte. Fine. Okay, and now let us assume that t1 has updated the value of a. So t1 loads this into the cache line. This is a, which is 4, this is 4, and then it updates it. Okay, so what happened when they updated? So whenever t1 updates, let's say a, let's say it made it 5, and let's say another thread t2, it comes access this variable b, and then it updates b. So let us assume it is on the same cache line. Now this time b will update this value 4. Now when it is updating 4, it is invalidating the whole cache line, right? When t1 updated a, it invalidated this cache line. When t2 is updating b, it again will invalidate this cache line, right? Because the thread when update, they obviously, if you assume 64 byte and a cache line of 64 byte, they will invalidate that same cache line of 64 bytes. So two unrelated independent variable, by virtue of being on the same cache line and different threads modifying them frequently, even though variables are logically unrelated, and coherence operates on the whole cache line, so the line keep bouncing between cores, and this can degrade the performance in high frequency system. Okay, so if one thread updates a, another thread updates b, both fall on the same cache line, performance may suffer, because every time what is happening is, whenever you are updating a, since b is also on the same cache line, you are invalidating that cache, right? So you are causing this ping pong and cache eviction every time, and this is called fault sharing, and this concept is very much important. Okay, now okay, so how do you get rid of this fault sharing? One way to get rid is that you keep them on separate cache. How do you keep them on separate cache? You can add some padding here, right? You can actually add some padding, so you can add the alignment and say that this is 64 byte alignment. By doing this, you can get rid of this thing, but there are other ways also, and there are trade-offs also. Okay, but just keep in mind, we can actually use padding to actually separate them on different cache lines, and once they are on different cache lines, whenever thread is updating a, it is not invalidating the cache where b is stored, and when thread t2 is updating b, it is not actually invalidating the thread where a is kept, right? And I assume that you are understanding what invalidating is, right? So whenever you are updating some value, uh, then the whole cache has to be updated, right? Because you loaded a value, you updated the value, you have to write back, and then when you read, the whole cache gets invalidated. You can read about it more. uh, let us see what else we need to discuss. Okay, so did we discuss lock free? Okay, so let us say an algorithm is lock free. So the conditions are, only if the system as a whole keep making progress. That means in finite step, at least one thread will complete its operation. So this is a kind of progress guarantee, no, not merely some kind of heavy implementation style. Okay, And lock free also does not mean that this is going to be very fast in all the cases, because under heavy contention, lock free algorithm can still perform purely poorly due to retries, due to cache line contention. Okay. Okay. And so, for example, an atomic increment using hardware CPU level instruction, that may be lock free. Okay. So keep in mind, whenever the terminality is lock free, it essentially means that system wide progress is guaranteed, meaning at least one thread completes in finite steps, even if others keep on retrying. Okay. So these are little bit complex to understand at first instance, but as you keep on no reviewing them again and again, you will get a hold of them. Next is wait free. mm, mm, Wait free. Okay. So again, wait free is an algorithm. An algorithm is wait free if and only if every thread completes its operation in a finite number of steps. And earlier what we had is at least, I mean, in lock free, at least one thread will complete its operation. In wait free, we have that every thread completes its operation in finite step. This was every thread. So by the definition of it, it appears to us that wait free is a stronger guarantee than lock free, which in turn means that wait free algorithms are harder to design and are very less common in general application code. For example, when I write code for my HFT systems, I usually go for lock free, because wait free are very difficult to realize. You're not will not actually realize that you're writing a wait free code. Okay. So wait free means that every thread is guaranteed to make progress in finite bounded steps, and it's a stronger guarantee than lock free. Okay. One more thing that I wanted to discuss before we jump into atomics was the relationship between lock free and atomic. So lock free does not mean atomic, and atomic does not mean lock free. And this is a very important clarification that I wanted to make, that an atomic operation gives atomic semantics on a specific memory. So let's say if there is this one memory, so the atomic operation gives atomic semantics on this specific object. So this does not automatically make the overall algorithm lock free. This is atomicity guarantee on this one memory location. This does not mean that the algorithm is lock free. And the C++ standard also does not guarantee that every atomic type is implemented without locks on every platform, right? So that is also there to keep in mind. Okay. So atomicity is about being indivisible operations, and lock free, wait free are basically progress property of algorithm. They should not be conflated with each other. Okay. Then let us address the elephant in the room, mutexes. Mutex is basically a synchronization primitive. It provides mutual exclusion to a critical section. So it protects a critical section so that at one particular time only one thread can access it, another thread is blocked. And this is different from atomics. Atomics are usually for a single memory location, but mutexes are for protecting long, large invariants across multiple variables, multiple steps. Okay. So, and mutex seems very intuitive and clearer and safer choice in many cases. Okay. Okay. So now next, what is this? So we now have understood, at least have got a slight idea of what a thread is, how cores and caches work, why visibility is delayed, how compiler and CPU reordering happen, what a data race is, what atomicity means, what ordering means, what happens before means, and why synchronization is necessary. Okay, now we are at a much better place to understand atomics. Okay, so just the concluding remarks would be that atomics are not just threads of integers, they are the C++ language tool that lets us express safe concurrent access while controlling atomicity, visibility, ordering with different strengths. And this is where the real atomic section begins. Okay, so before atomics, you have to think in terms of thread sharing memory across cores, each core having cache, store buffers, plus compiler and CPU reordering. Without synchronization, concurrent conflicting access cause data races and undefined behavior in C++. Atomics gives a formal way to avoid that, and while controlling atomicity and memory ordering also. So the key correctness relationship that you should look for is uh, that memory visibility, the C++ memory model, and that happens before. Okay, uh, I would rest it for today, and what I want is whatever different jargons that we have read, discussed about this in today's lecture, I want you guys to once again go through it, take a note of it. See, there are limited number of jargons, some 20-25 jargons are there. Don't uh, over explore a lot at this stage. First try to get a blanket understanding of different things, and then slowly it will come to you. If you think that you are going to master these terms like in a single shot, that's not going to happen, because it is coming from my experience. I have been working with these for last 5 years, and still I feel sometimes unfamiliar to these things. Okay, so there is no issue if it came as a surprise to you. It came as what is this? Okay, so it's so from the next lecture would be about atomics. We will understand each and everything about atomics. We will write a simple program where we will understand how atomics actually helps in enforcing the C++ memory model of reordering, of memory visibility, of happens before, and single variable synchronization. So we will create a simple program where we will compare mutex with synchronization. We will create a program and we will create a hot path. Then we will try to implement a locking strategy design pattern where we will, in the context, we will pass first the atomic strategy, then the mutex strategy, and let's also add a policy based, I mean template based strategy. So, and then we will do the benchmarking, and then we will understand what actually is happening. We will try to measure the latency. We will try to measure the P99 95 latency. We will see the distributions. Okay, and yeah, so just read about the strategy design pattern and also the policy based design. Those are very much important when you are picking a strategy, when you are picking an algorithm at the runtime. You use a strategy design pattern, and so it has some overhead, because at runtime you are you're picking this with the help of virtual dispatch, so there is a level of indirection and some overhead will be there. Hmm, but yeah, there are trade-offs. So we will also see the policy design pattern, and we will finish this atomics and the concern design patterns. So I like to teach in a very integrated manner, and this is my first lecture that I'm recording. And in the lecture, at some of the point, I thought that I could have done more better, but I think this is a learning for me also. Like knowing something and explaining that to someone is a different piece of cake, which I totally understood today. But definitely, I'm going to improve on this. Uh, I'm going to reinforce all the facts, all the jargons that I taught you today. In next lecture, in atomics and design patterns, I will actually enforce all these concepts, actually make them visualize you in practice how it's going to happen with a simple program. Okay, so next lecture will be a practical visualization of all these concepts, and how we can achieve all these using atomics and mutexes, and what are the trade-off between atomics and mutexes, and in which scenario we would prefer atomics and mutexes. And so there uh, Actually, so one of my projects which involved heavy simulation engine, where we were doing some event driven simulation in a hot path. Since the code had been written some 20 years ago, they were using some mutex in a hot path and for a simple variable. And so I ran some benchmarking. I ins- uh, employed a strategy design pattern there, and I added atomic strategy. Then I moved to policy based design. So that was a learning curve for me also, and hopefully I would be able to transfer all those knowledge to you. These are very much used in production in the industry, and you should have a clear grip on these concepts. Signing off for today, CPP Valley.